On this DeBacco University video, I'm going to go over the light emission spectra. So all these different lines that you see, going to be explaining them so you can develop a better understanding for what these are actually showing you. All right, let's get into the light emission spectrum. So this is a unique pattern of light wavelengths emitted by atoms or molecules when they release energy. It's like a fingerprint for each element, and no two exact are alike. And what's really interesting is that when we see that light emission spectrum, we can go back, we could start to identify what element or what molecules essentially made that light. And this is really great for studying things that might be very distant, like stars. We can see what light they're emitting, and we can determine what elements they might be made of from that. So kind of an interesting way we can utilize this. Now we also have something called the light absorption spectrum, and this is a visual representation of how a substance absorbs different wavelengths of the electromagnetic radiation. This shows which colors, or directly related to what energies of light, are absorbed and which pass through. So here we see the absorption. We have a high density hot matter, cold gas, we got a little area here. And we're looking at what areas are absorbed. So we see those black lines there are showing the areas of absorption within that continuous spectrum. Now when we're looking at light, it does relate essentially to energy. So when an atom absorbs energy, typically from heat, electricity, or radiation, the electrons jump up to other energy levels. So if we think about this kind of with the Bohr model, we have these different energy levels. We have, depending on what energy or how much energy the electron is absorbing, it'll jump up to a different energy level. Now we don't really see that. There's not really evidence of that we can visually see. What we do see is that when the energy is released, or these electrons start to fall back down, they're releasing that energy in the form of photons, or particles of light. The wavelength or color of each photon depends on the energy difference between the levels. So if we look at here, just as a little example, if it absorbed enough energy to get from energy 2 to energy 3, and then it drops down, well, that's going to emit the longer red wavelength. Here, if it goes up to level 4 and it drops down to the ground state here, or at level 2, we'll see a green light. And if it jumps up to the highest, we can see it would jump down all the way and it'll produce a violet light there. So we can see the different colors are directly related to that energy being absorbed, because that's changing the wavelengths. As a reminder, red wavelengths has a very long wavelength compared to blue or violet here having very short high energy wavelengths. Now, this all depends really on that visible spectrum. And this is the portion of the electromagnetic spectrum, which is a long thing. We get a very small portion of that the human eye can detect. Typically, that's between 380 and 750 nanometers. Shorter wavelengths, again, in that 380. Longer wavelengths in that 750. Those shorter wavelengths are going to be more of those kind of purple or violet colors. And those longer wavelengths are going to be more of those red colorations. As we can see here, ultraviolet, infrared is what we can't see. This is that visible light spectrum where we can observe and see those different colors. So types of emission spectrum, there are the line spectrum, as we can see basically right down here. Bright lines on a dark background seen in gases like hydrogen or neon. Each line corresponds to a specific electron transition. Then we've got the band spectrum, and the middle one shown here. And these are groups of closely spaced lines, often from molecules undergoing vibration or rotation transitions. So vibrational or rotational transitions, not used as much. And we have this simple continuous spectrum at the bottom there. And as we can see, this nice smooth blend of all the wavelengths, like the light from a hot filament or the sun, you'll get that nice continuous or full band spectrum. Now the line or bright line spectrum, as we can see here, this is where we're looking at now starting to see those fingerprints, or those identification of those different elements. This is a series of distinct sharp lines of color against that dark background, so we can start to see those individual lines very well. This is caused by the emission of individual atoms, typically gases, when electrons drop from those higher energy levels to lower, as I showed you, and depending how much energy, that's where we're seeing those different colorations. An example here would be hydrogen's Balmer series, which is red, blue, green, and violet lines. It's just unique fingerprint. We can see the others here as well. The reason why I'm showing you all these, this is used for identifying elements in stars, gas lamps. Each element has its own unique fingerprint. We can see that when we put them all together, well, it might be a little hard to see them all individually. When we start to look at them as different lines in comparison, we can definitely see, wow, those little barcodes might be slightly different there. And that's how you can think about these as little barcodes for the individual elements. While initially they all look quickly the same, when you start to really analyze them, you can see the distinctiveness and the uniqueness of each element, especially when you compare them from one to another. Now we've got that band spectrum. It's a little bit more complex, comes from molecules, usually not single atoms. This is a series of closely spaced lines that blend into that color band. It's caused by the molecular transitions, especially again those rotational vibrational changes. The spectrum of gases, likely oxygen or nitrogen, or compounds like titanium oxide and cool stars. It's used for studying molecular structure, temperature, composition of planetary atmospheres, or combustion analysis. Think of this more, instead of like a barcode, think of this more like a watercolor painting. It's detailed, layered, enriched with those each molecule little nuances there. And we get to that continuous spectrum, which is the smoothest spectrum with no lines or no gaps. As the name implies, it is continuous, it is seamless, and it's spread over all wavelengths in a given range, made by hot, dense objects like stars, incandescent bulbs. Usually the sun is what we're most familiar with, or glowing metal filaments in some cases. This is understanding black body radiation, temperature, as well as energy output. Imagine a rainbow with no missing colors. It's pure, basically uninterrupted light, showing all of those wavelengths in that continuous spectrum. So if we kind of summarize these three here, even though I covered them in a little bit more detail, here's that nice little summary of seeing what they're actually looking at, what the source is for those, what the appearance would be, as I tried to show you some visuals, and ultimately what they're used for in science. So as we can see, these can be utilized to help develop a greater understanding of both things that might be really close to us, as well as very, very distant planets deep in the ends of space.